Okay, so today I intended to talk about monoidal model categories. So first of all, to talk about monoidal model categories, we have to talk about monoidal categories themselves. So I will start from just monoidal categories. And today my talk will be very expository. I will just state definitions, maybe give some examples, but in general, this all is very well known. We already talked a bit about monoidal categories before, so today I will just recall some very basic facts. Okay, so definition. Monoidal structure on a category is first of all a functor, which is usually denoted as tensor product from C times C to C. Unit object S. I think that the name comes from the fact that usually one considers spectra, and in spectra, the unit object is precisely the spectrum of a sphere, the sphere spectrum. Yeah, so the unit object, an associator, which says that this monoidal operation is associative. And left and right isomorphism of unity. So left for an object X is the following isomorphism, and right is clearly an isomorphism, but from other side. And also we should have some coherence diagrams, meaning that, for example, if we take, so if we take, for example, I don't know, X times S times S, it is the same thing as just X. And so we can write similar diagrams to impose all the coherence conditions. So here, or for example, if we write like this, so we have various diagrams which say that all these operations in monoidal category are coherent. And so let me give an example of a monoidal category. The most basic example is just category of sets together with usual product. This example can be enhanced. We can consider simplicial sets also with the operation of taking product. Or we can consider, for example, category of B modules over commutative ring R and operation of tensor product. Okay. So now, since we've defined what is monoidal category, we must define functors between such objects. So here comes the definition of monoidal functor. So we have two monoidal categories, C and D. And we say that a functor is monoidal if we have a triple. So monoidal functor if f from C to D is just a functor. M is a natural isomorphism, which says that monoidal multiplication is compatible with functor f. So and finally, alpha says something about the behavior of unit objects. So actually, f is maps unit object in C to a unit object in D. So that's an isomorphism. And of course, we once again have coherence diagrams, which say that everything should be associative, everything should be compatible. Yeah, so plus coherence diagrams. So let me give another example. Assume that we have a category of sets, and we go to our modules, where R is commutative. I'm sorry, above, I must have made a mistake because here R is not necessarily commutative. That's why we need bimodules. Otherwise, modules over commutative ring are canonically isomorphic to bimodules. So we actually, they're not canonically isomorphic, but we can make any module a bimodule by considering this symmetric multiplication. So here, actually, R is not necessarily commutative. And here R is commutative, and we consider a functor which maps a set X to a free module generated by this set X. And so here it is important that R is commutative, and we get a monoidal functor because, if we have a product of two sets, then it is mapped to this thing here, and this thing here is precisely then the product of two modules. And of course, the unit of this multiplication is just a singleton set, and it is mapped just to R of singleton set, which is canonically isomorphic to just R, which is a unit of our tensor product multiplication in modules. Okay. So another example, which is familiar to us, comes from simplicial sets and topological spaces. So we may consider simplicial sets together with product operation, and we have geometric realization functor, which goes to compactly generated topological spaces. Then, of course, if we have a product of two simplicial sets, it goes to the product of realizations. So no surprises here. Now, since we've defined monoidal functors, we want to define monoidal natural transformations between such functors. So let me give another definition. Given two functors f and f prime from C to D, monoidal natural transformation tau from f to f prime is a natural transformation of functors which is compatible with M and alpha. And that means that we have the following. So we have this identity. So an isomorphism between units is compatible with natural transformation on units between. So this is an isomorphism of units for the functor f prime. This is the natural transformation. This is an isomorphism of units for the functor f, and they should pass to one another after natural transformation. And for compatibility with them, we must have the following commutative diagram. Okay, so that's the definition of monoidal natural transformation. And given monoidal categories, monoidal functors, and monoidal natural transformations, we can organize them all into a two category of monoidal categories. Consisting of monoidal categories, monoidal functors, and monoidal natural transformations. So these are the objects, these are one morphisms, these are two morphisms. Now we can, so the basic progression here is very same as in algebra. We start from something that should be thought of as analogous to rings. Monoidal categories are just rings in the world of category theory. Speaking in some highbrow terms, monoidal categories are just ring objects inside of well, I'm sorry, that's not true. they're monoidal objects inside of category of all categories. Still, the idea is that monoidal categories are somehow analogous to rings. Now we pass to commutative rings, which are symmetric monoidal categories. Then we will discuss modules over rings, which are just modules over monoidal categories, and so on. So now we discuss symmetric monoidal categories. Let me give a definition. Plus the following usative diagrams. So since we're talking about bifunctor of tensor product, we can consider a swap operation on a tail, which just interchanges arguments. And this thing here should induce a functor inside of the category C itself. So here we have tensor product. And yeah, of course, since we have this operation, we also should have coherence diagrams. But the basic idea is that we just have an isomorphism which interchanges arguments. Okay, so basically all of the categories above, so example, so all of the above except bimodules over non-commutative ring are symmetric monoidal. Well, once again, no surprises there. It is clear that we can interchange factors in direct product of sets and obtain something isomorphic. Now we should, in a similar way, we should define a symmetric monoidal functor. So first of all, it should be monoidal. And second, the following diagram commutes. Yeah. So that's an example of, so that's the definition of symmetric monoidal functor. An example of symmetric monoidal functor was already given. And in fact, it's just a functor-free module. So we have a functor to modules over commutative ring, which maps X to the module freely generated by X. Another example is, of course, simplicial sets, which are mapped to compactly generated topological spaces. Here we also have a symmetric monoidal functor. Let me give you a non-example of symmetric monoidal functor. So consider the graded vector spaces over a field K. So characteristic of K should not be 2, should not be equal to 2. And so graded tensor product gives monoidal structure. And we can define this swap operation in two ways. So T of x, y is just yx, or T of xy, which is probably more familiar, is -1 to the product of gradients. Of course, both give us a symmetric monoidal structure on the graded vector spaces, but the identity functor between them is no longer symmetric monoidal. And what breaks down is precisely this diagram. So we no longer have, well, we no longer have commutativity for obvious reasons. So that's why we need that characteristic of the field is not 2. Okay, so we discussed rings. Now it's time to go to modules. So, oops. Okay, so let me give you a definition. So let's assume that C is a monoidal category, then write C module is a category D plus the following tuple. So we should have a bifunctor from D times C, which is precisely the action of the monoidal category C on this category D. A is an associator, so it is a natural isomorphism between the following two So now the tensor product here means different things. Tensor product here and here is the tensor product of this action of C on D, and here the tensor product is an internal tensor product of C. So R is the natural isomorphism which says that action of unit element is trivial. So, yeah. And of course, we'll also have coherence diagrams. But yeah. So let me give you an example of coherence diagram. For example, we should have the following. So this one here is just a D tensor, the left unit inside of a monoidal category. Here we have an associator, or rather an associator to the power -1. And here we have R tensor AD. It's not very good that we have, well, let me write it like this. Then it makes sense. Okay, so that's an example of coherence diagram. I just needed to give it because I'm always talking about coherence diagrams and no one ever seen one. So let me give you one. Okay. So let me give you an example of module structure. Assume that, well, basically any category C or better D. Assume that D is a co-complete category. Then D has a structure of set module. So the tensor product is given by, actually, in the last talk by Arseny, it was a common theme that we used this dot product to form this co-product of A copies of X. So if A is a set, it acts on any category on any co-complete category by taking this co-product. So we have this, and that gives us set module structure. Okay. So now we need to define functors between two C modules. we assume that we have two C modules, functor, or better still, C module functor F from D to E is a functor plus natural isomorphism which says that the functor should compute with the action. And so such that we have coherence diagrams, commutative, obviously. So let me give you an example of coherence diagram. So we have, for example, a coherence diagram like this, and you can draw another coherence diagrams in a similar fashion. You just put everything you want to be associative and coherent with the functor in the diagram, and you get a coherence diagram. So I'm not writing all of them down because it just take a lot of space, but won't clarify a lot of things. Okay, so now we're ready to define what is, yeah, and obviously, so let me give a short note about this. Note that a functor between co-complete categories is a set module functor if it preserves co-products. Well, this is trivial because, as it was said earlier, the canonical structure of set module in a co-complete category is just this thing here. So obviously, this is the same as requiring that the functor preserves co-products. Okay, so now let's move on to natural transformations between functors of C modules. Natural transformation between C module functors is, well, a natural transformation between functors such that the following coherence diagram computes. Okay, so let's step down. Yeah, so this is an example of a coherence diagram. Now, let me give a definition of algebra over monoidal category. So it could be a monoidal functor from C to D, which is akin to the unit in usual algebra. Yeah, plus, so yeah, of course, D should be a monoidal category. D is a monoidal category. We have a monoidal functor I from C to D, and C algebra is just with the algebra structure on it. So now, since I've defined what is a C algebra, I can now define a C algebra functor. So the functor between C algebras is just monoidal functor from D to E, where D and E are C algebras, plus monoidal mutual transformation. Well, isomorphism.
C algebra structure is just a functor, yes?
Yes, yes. So C algebra structure is monoidal structure on the category D plus the functor. So it's very similar to plus monoidal functor. So it's very similar to when you define a usual algebra, you say that it's basically a ring plus a homomorphism of rings from the ground ring to this ring. So yeah. Yeah, okay. So we should have a monoidal natural isomorphism between two functors of C. Yeah, so we should have a monoidal natural isomorphism between these two functors. So similarly, we define a natural transformation monoidal transformation. So from F to F prime, such that the following diagram computes. Okay. So I think, yeah. So let me give you an example of C algebra structure, C algebra functors. So C is a category of left are modules. So just let me denote it like this. Over commutative ring R. And let S to T be a morphism of two R algebras. Then have a functor from S modules to T modules, which just maps an S module to T module, which is formed by induction. And so what is, well, first of all, we have, obviously, we have a functor I from R modules to both of these, which is induced by the following. So we have a homomorphism of algebras over Z from R to S or from R to T. And so we obviously have an induced homomorphism, an induced morphism between categories, so induced monoidal functor between categories. And we can see that we get, so this functor here is also monoidal, and it is a functor of C algebras because we have the following isomorphism. So if we take this consecutive induction, we obtain something which is canonically isomorphic to TRM, which is precisely I mod T of M. So yeah, we have we have a functor of C algebras between these two categories. Is this example clear?
Yes.
Great. Then I think we can make a break and reconvene in 5 minutes. So I described an example of functor between two C algebras. And now I want to give another definition, which is related to particular case of monoidal categories, to symmetric monoidal categories. So the definition. And symmetric C algebra structure on D is a symmetric monoidal structure on D plus symmetric monoidal functor from C to D. Okay, so basically we describe the commutative algebra over a commutative ring. So definition. Between symmetric C algebras is a symmetric monoidal functor plus functor of C algebras. So yeah, I think I should give an example. obviously we have a symmetric monoidal structure on simplicial sets. And this symmetric monoidal structure is a set algebra. So it's a set algebra. So we have a morphism from monoidal functor from sets to simplicial sets, which sends x to x delta to discrete simplicial set on x. And we have, obviously, this functor is monoidal because x times y is mapped to product of x delta, y delta. So this gives us a structure of set algebra on simplicial sets. Okay. Now we're ready to define what is a central C algebra over symmetric monoidal category. So it was somewhat forced condition that this symmetric algebra should be commutative. So we can drop this condition and define what is a central algebra, meaning that a monoidal category over which we're considering certain algebra lies in the center of this another category, of this other category, but this category, the category itself needs not to be commuted. So let me give another definition. So we start from an ordinary algebra structure on D. Algebra. So this is precisely the condition that the image of C commutes with all elements of the category D. This satisfies coherence conditions. So there are several of them. Let me write them down once in a while. So yeah, the condition number 0 is obviously the fact that this transposition squared should be identity. Okay, so obviously, yeah, the central C algebra is just a category with this structure. Now, let me give you an example of central C algebra. Let H be a Hopf algebra, for example, ring algebra. Then mod H is the vector algebra. For these reasons, we can tensor any H module with a vector space, and this automatically becomes another H module. And of course, we can embed the category of vector spaces as trivial H modules inside of the category of all Hopf algebra representations. And so this is always a central vector algebra, but it is symmetric if H is co-commutative. Okay. So now,
And I is an inclusion of vector space as trivial. Okay.
yes. Okay, so now we want to define a functor between central algebras. So assume that C is a symmetric monoidal category. But the algebras C is a functor of central C algebras. If it is a functor of C algebras such that the following diagram is commutative. Okay, so that's the condition that a functor is a functor between central C algebras. And yeah, so we can look at it and think a bit. But basically, the idea is simple. We just require that this transformation T commutes with the functor F. So that's basically it, although the diagram looks quite scary. It has 6 terms instead of usual 4. But that's basically the idea is very simple. We just require that I computes that T computes with F. Okay, so now we will do something a bit different. We will talk about closed monoidal categories. And so the reason for this shifting of gears is the following. So we had everything organized into 2 categories with functors as 1 morphisms and natural transformations as 2 morphisms. But actually what we want is, and that comes from theory of model categories, is that we want to consider, instead of functors, we want to consider adjoint pairs of functors. So we had the Quillen adjunctions, and we want here, we also want to consider adjunctions as morphisms. So this is the reason why we're shifting gears now, and now we will talk about adjunctions between monoidal categories and about closed monoidal categories. So the definition of closed monoidal categories comes naturally when we consider adjunctions. But let me not get ahead of myself. I will first describe what is even an adjunction between monoidal categories. So it's quintuple, but I wrote it down as 5-tuple because I'm not even sure that I'm saying it right. So we have this quintuple consisting of tensor product, 2 home functors, 1 for the left and 1 for the right, and 2 natural transformations. So let me give it in a bit more detail. So tensor product is always a bifunctor from C times D to E. Home right is a bifunctor from D opposite times E to C. Home left functor is a functor from C opposite times e to d. And here phi r and phi l are natural isomorphisms in the following form. So basically, we're writing tensor homojunctions, but in a very abstract setting. That is why we required this by functors and stuff like that, but actually it's just a tensor homojunction without any real meaning to tensors or homes. Yeah. So that's what an adjunction is. And now let me define a closed model category, closed monoidal category. So this quadruple is just monoidal structure on C, and this quadruple is an adjunction from C times C to C. So basically, what that means and what the word closed means is that we have home objects. We have home objects inside of the category C, although we have to distinguish between right and left home objects. But basically, that is precisely what this definition requires. Okay, let me give an example. So in sets, we don't have any difference between left or right objects. We just get this power set. So in our modules over commutative R, we have a closed monoidal structure given by just the usual module of homomorphisms. So another example which explains why we're so obsessed with compactly generated topological spaces is this category, compactly generated topological spaces. And the reason is that when we take the usual power set or topological space of maps, mapping space, it is also compactly generated in compact open topology. Unlike for general topological spaces where the mapping space may not be Hausdorff. So yeah, that's the reason. So compactly generated topological spaces. Okay. So now I'm ready to give a definition of what is a closed monoidal functor.
Is there exist an example of two homes which are different?
Yes, yes, there is an example, although I don't understand it, but I can give one. So one moment. So there is a closed monoidal structure in bimodules of a non-commutative ring. But here, home left and home right are different, although I don't understand why, or I don't even understand how this home spaces, home modules should look like. But I guess if we try the usual formula and take homomorphisms over R from X to Y, no, I actually I don't know how to proceed with this example. So but I know for sure from Hovey's book that this is an example where left and right home modules are different. Okay. We can figure it out later. Okay, so a closed monoidal functor between closed monoidal categories is a quintuple where Fm alpha is a monoidal functor, and Fu phi is an adjunction. Let me give you an example. So if we consider functor between two categories of modules, that looks like this. So we have a homomorphism from R to S. So that's just an induction. We actually have a forgetful functor in another direction, which forgets multiplication by S and remembers only multiplication by R. And so we can form an adjoint pair, which consists of these two guys. Okay. So the last thing I wanted to talk about today was the difference which occurs in the case when we consider closed symmetric monoidal categories. So first of all, in the symmetric case, we can interchange elements in the tensor product. Therefore, right and left Holmes do not differ. So that partially explains this example where we had modules over non-commutative ring because this category itself was not symmetric, and therefore right and left Holmes should be different, although I still don't know how they look. So yeah, that's the first thing. The second thing is that on two category of closed C modules, there is a duality. So this duality works like this. We just take an opposite category and we construct a C action like this. Note that we can drop this subscript R here because there is no difference between left and right Holmes for symmetric categories. Yeah, if the category D is symmetric, although it is not always true because actually we just consider modules and we don't have any requirement about modules being symmetric. So we should write this subscript here. And so the closed structure is given by the following. So xk is mapped to x times k, and xy is mapped to left home from y to x. So associativity in D in the dual model corresponds to the isomorphism. Yeah. So this duality always obviously extends to functors. So if we have an adjoint pair, which is a morphism between D and E, then we can construct an adjoint pair in the opposite direction, which looks like this. So we interchange the functors, we take the inverse natural transformation, and we take this dm to the power of -1, where dm is a natural isomorphism from U of kx to R of kux. Yeah. Okay, so that was all I wanted to talk about today. I think we should finish here. Next time I will discuss, I wanted to discuss monoidal model categories. And the time after that, we will discuss homotopy category of monoidal model category. I think that's it for today. Are there any questions?
Okay, thanks a lot.
Okay, let me stop the recording.